Ophir Spiricon is the global leader in precision laser measurement, with over 30 years of product innovation, including Ophir power meters and sensors, and Spiricon and photon beam profiling systems. Now part of the Newport family of world-class photonics brands. For welding and ablating, a flat-top beam with a larger spot is often preferred. A Gaussian beam may have the same power as a flat-top beam, but the spatial intensity of the beam profile will yield dramatically different results. To control your beam, you must measure your beam. Laser beams are defined by 4 fundamental properties: waist width, divergence, wavelength, and power or energy. However, knowing these values makes it complicated to know how one laser may perform compared to another. 2 of these values, waist width and divergence, can be used to calculate m², the measurement indicating how closely a laser beam's mode content correlates to a pure TEM00 beam. A laser with only TEM00 mode content has a m² value equal to 1.00. The m² measurement allows the user to relate the quality of their beam to how a true TEM00 beam would behave in an optical system. TEM stands for Transverse Electromagnetic Mode, where electric and magnetic field vectors are both normal to the direction of propagation. The digits refer to mode content, where higher values indicate higher modal orders. All laser beams consist of mixes of various modal orders. Control of the mode mix is one of the goals of the laser designer. A laser designed for diffraction-limited focus is one that approaches a purely single-mode TEM00, where the m² value approaches 1.00. A higher modal content will yield an m² value greater than 1. Thus, the final m² value of a laser depends on the percentage of all modes present in the output beam. In simplified mathematical terms, a beam with an m² value of 1 will focus to as small a spot size as the wavelength and a distortion-free lens can achieve. Lasers designed and manufactured for applications that are frequently used for drilling, cutting, and welding are often designed and tuned to have low m² values. And today, most manufacturers specify the best possible m² value of their laser. Spiricon and photon beam propagation analyzers are most often used to make this difficult measurement. The closer a beam's m² is to 1.0, the more tightly the beam can be focused, delivering more energy in a smaller spot. If your application requires an m² near 1, and your laser beam is an m² of 2, your power density is 1/2 of what it could be, and it will focus to a spot size 1.414 times larger. The smaller spot will yield peak power densities greater than the one with a higher m² value. This can mean a number of improvements to the user, such as smaller drill hole sizes, thinner or deeper weld lines, processing thicker materials, less power consumed, and greater working speeds. Frequently, the anticipated results do not materialize. Often this can be predicted if one knows the m² value of the laser versus power output levels. To demonstrate this problem for a hypothetical beam of 1 joule per pulse and m² equals 1.0, with a focused average power density of 100 joules per centimeter squared. If we increase the power by 50%, but the m² degrades to 1.5, power density falls to 66.6 joules per centimeter squared, a reduction of almost 1/3. This reveals an all too common result, where more power input results in less work getting done. There are many factors that influence the beam profile and m² of a laser. For example, poor quality optics, spherical aberration of lenses, diffraction caused by apertures, thermal effects of the gain medium, and parasitic reflections may all degrade the quality of the laser beam. The alignment and quality of the optics of the laser resonator, as well as of the optical train in use once the laser beam has emerged from the cavity, can all affect beam quality. Poor beam quality can limit the power scalability of high-gain nonlinear devices. Laser fluence levels strongly affect the efficiency of nonlinear frequency conversion devices, so that high-quality beams produce the most desirable results. A high-quality beam can also allow for a larger distance between the focusing objective and the work surface. In fiber optic communications, beams with an m² close to 1 are required for coupling to a single-mode optical fiber. Again, if you cannot measure your beam, you cannot control the outcome. Many of today's DPSS, diode-pumped solid-state laser manufacturers use Spiricon and Photon automated m² measurement systems to ensure the beam quality of their lasers. Laser system developers measure the quality of their beams in real time as they make adjustments to their laser cavity design, laser optics, and other important design criteria. These scientists require the accuracy and flexibility the Spiricon and Photon beam propagation analyzers provide. Customers and users of these laser systems employ either the Spiricon M²200S or the Photon 1780 to assure the lasers they are receiving have the beam quality that they expect. These customers find the high throughput speed and accuracy of these instruments essential to the success of their operations. Spiricon and Photon products are known for accuracy and ease of use. Using our patented UltraCal calibration method and auto-aperturing to exclude noise beyond the wings of the laser beam, you are assured the most accurate beam measurements in the industry. In fact, UltraCal's baseline correction algorithm was used to help establish the ISO 111463 standard for beam measurement accuracy. The Spiricon M²200S allows laser researchers, laser manufacturers, and high-volume laser purchasers to ensure their lasers are the highest quality possible. The Photon MS1780 provides accurate high-speed m² measurements most often needed in a production environment. For over 30 years, Ophir Spiricon has met the challenge to consistently provide accurate and reliable laser measurement devices. Measuring your laser has never been easier. Ophir Spiricon Photon, the true measure of laser performance.